Welcome to CSC 201, Lesson 5.2, Mathematical Induction. A proof by mathematical induction is analogous to proving we can climb a ladder using a two-step process. So I want to prove that I can climb a ladder. Step one is called the basis step, and I just have to prove that I can get myself on the ladder, that I can step onto the first rung. Step two is called the induction step, and it says that I need to prove that if I'm on any generic rung of the ladder, that I am capable of getting to the next rung. So if I can prove that I can get on the ladder, and I can show that I have the capability of moving from one rung to the next, that should prove that I can climb the entire ladder without having to show you every single step, right? So if you had a small child and you wanted to make sure that they were capable of climbing a ladder or climbing up to the top of the slide that's really high, right? They need to show you that they can get onto the first step, and then they would need to prove that they are capable of going from one step to the next. You don't need to see them do every step. If you know they can get from one step to the next, you know that they can get to the top of the stairs. Okay, so let's look at an example that we're going to prove using mathematical induction. But first, we're just going to study it a little bit. So we have a formula for all n bigger than or equal to 1. If you want to sum the first n integers, you can calculate that with a formula, n times n plus 1 over 2. So let's verify that the formula holds for n equals 1 through 4. So for n equals 1, it says I'm adding up the first one integer, right? So 1 plus 2 plus 3, but n is 1, so I'm stopping at 1. So for n equals 1, I just have 1. And then does that equal the right-hand side, which is I'm replacing the n's in the right-hand side of this equation with 1's. So I have 1 times 1 plus 1 over 2. And I do get 1 equals 1 times 2 over 2, which is 1. All right, let's check it for n equals 2. So I'm going to add 1 plus 2, and I want to know, does that equal, plug 2 into the formula, 2 times 2 plus 1 over 2. And I get 1 plus 2 is 3. Here my 2's cancel. 2 plus 1 is 3. Checks out. N equals 3. I'm going to add 1 plus 2 plus 3. And I want to know, does that equal 3 times 3 plus 1 over 2? So 1 plus 2 plus 3 is 6. And 3 plus 1 is 4, times 3 is 12. So 12 over 2 does in fact equal 6. So it holds for n equals 3. Does it hold for n equals 4? So I have 1 plus 2 plus 3 plus 4. And I want to know, does that equal 4 times 4 plus 1 over 2? So I get 10 equals 20 over 2. Check. So it holds for n equals 1, 2, 3, and 4. We need to prove that it holds for all n. And I'm going to use this ladder analogy where I'm going to show that it's true for the first value of n equals 1. That's that I can get on the ladder. So I can get on the ladder. I know that it's true for n equals 1. So we already wrote it out above. We have 1 equals 1 times 1 plus 1 over 2. Formula is true for n equals 1. Okay, that step is done. The basis step, I can get on the ladder. Next page is the induction step. So in the induction step, we need to show that we can get from any one generic rung of the ladder to the next. That if I could get to the kth rung, then I am completely capable of getting to the k plus first rung. It has to be generic. You can't say, well, I can go from the 4th to the 5th, or I can go from the 2nd to the 3rd. It has to be a generic kth rung of the ladder. I need to show you that on any generic numbered rung that I can get to the next rung. So what we do is we're going to show that if the formula is true for n equals k, k being the generic rung, that if I can get to the kth rung, then I can also get to the k plus first. Then it also has to be true for k plus 1. So what we do is we suppose the formula is true for n equals k. We just suppose it's true, and we need to show it's true for k plus 1. So we're going to suppose it's true for k. So suppose that 1 plus 2 plus 3 plus up to k does in fact equal k times k plus 1 over 2. Okay, and then we need to show that it's actually true for k plus 1, right? So that if I want to do 1 plus 2 plus 3 plus k plus 1, so you're going to go one further in the list of integers you're adding, that is equal to, okay, now if I'm plugging into the formula, it's the last number in the list, k plus 1, times 1 greater than that, which would be k plus 2 over 2. Okay, so that is for n equals k plus 1. So I'm going from 1 to k plus 1. So it's just make it real clear. K plus 1 is the last number in the list. So when I plug into the formula, I'm replacing this k, because that's the last number in the list, with a k plus 1, and this k with a k plus 1. So this becomes k plus 1, and k plus 1 becomes k plus 1 plus 1, which is k plus 2. So this is what I need to prove based on my assumption this. Okay, so suppose it's true for n equals k, show that it has to also be true for k plus 1. So let's see what we've got. I want to consider the sum 1 plus 2 plus 3 plus, go all the way up to k, and then add the one more, k plus 1. Okay, well that is, I can cut this chunk off. That part I have assumed that this formula will apply to. So 1 plus 2 plus 3 up to k simplifies to k times k plus 1 over 2. I'll leave it purple. Okay, so I have k times k plus 1 over 2. And then I still have to add this last term, k plus 1. And then I have two fractions to add. To add fractions, you need a common denominator. So I'm going to take this k plus 1 and write it over 1 and do times 2 over 2. And this is going to become k squared plus k. So I just distributed my k there. I did this distribution. And then I'm going to multiply this 2 times both terms in the k plus 1. So I'm going to have plus 2k plus 2 over 2. Now my fractions have the same denominator. I can add the numerators, and so I get k squared plus 3k plus 2 over 2. Denominator stays the same. And then k squared plus 3k plus 2 factors to k plus 1 times k plus 2 over 2, which is what we needed to show, right? I needed to show that this sum added to k plus 1 times k plus 2 over 2. And I did it, okay? Assuming that the formula was true for n equals k. So I did need that assumption to show that this was true. But if I've shown that I can get on the ladder, I've shown this is true for n equals 1, and I've shown that if it's true for any k, then it's true for k plus 1, so that means that I can climb the ladder. I can step on at 1, and if it's true for 1, it must be true for 2, and if it's true for 2, it must be true for 3, and if it's true for 3, it must be true for 4, and so on forever. So it's true for all n. Okay, I'm going to do a little non-inductive proof of this formula. It's kind of fun, so I just thought that just an alternative proof to further convince you that this formula holds. Let's say I want to add up the first n integers. I would have 1 plus 2 plus 3 plus da-da-da-da. And I would stop at n, but I'm just going to say, well, I have n as the last number, but before that would be an n minus 1, and before that would be an n minus 2, like that. And we don't know what it adds up to. It has to add up to something because we know it's finite. So it has to add up to some number x. And then I know that sums are commutative. So I can write my addition in any order. So I'm going to reverse it, and I'm going to say n plus n minus 1 plus n minus 2 plus blah, 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 plus 3 plus 2 plus 1 also equals x. And then I have these two equations, and I'm going to add them together. Just a little algebra. You can add two equations together. And I'm going to draw some parentheses because I'm going to go term by term here, 1 plus n. Okay, so that comes out to 1 plus n. Plus, and then I'm going to do my 2 and my n minus 1. These two together add up to n plus 1. And then 3 and n minus 2, those also add up to 1 plus n. N minus 2 plus 3, 1 plus n. 1 plus n, 1 plus n, and that adds up to 2x. So I'm just going to put some parentheses here to sort of make it clear that I'm adding multiple copies of 1 plus n. Okay, how many copies of 1 plus n am I adding? Well, how many terms were there in the original series? 1, 2, 3, blah, 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 n. There are n terms in this series, which means I have n copies of 1 plus n down here. So I have n times 1 plus n equals 2x. And then if I want to know what x is, I just divide both sides by 2. So x is n times n plus 1 over 2. And there's the formula. Okay, so we'll just do a couple problems where we apply this formula that the first n integers added together is n times n plus 1 over 2. So first one, very straightforward. I want to add up the first 500 integers. So this would be 500 times 501 over 2, which is 125,250. Just plug it into the formula. 2 plus 4 plus 6 plus 50. So this is the first 25 even integers, which doesn't look like that, right? The formula I have is for the consecutive integers, not every other. So my little trick I'm going to do here is to factor out a 2. So this is going to be 2 times 1 plus 2 plus 3 plus ... plus 25. And that's going to be 2 times, and then I'm adding up the first 25 integers. So now I can just use the formula. So this would be 25 times 26 over 2. And that the 2's cancel. 25 times 26 is 650. Okay, 5 plus 6 plus 7 plus 8 plus blah, 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 all the way up to 50. So this is not the first 50 integers, right? Because I'm starting at 5. So I could add up the first 50 integers and then just subtract what's missing here. So I'm going to say, well, this is 1 plus 2 plus 3 plus blah, 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 plus 50. And then I have to subtract what I'm not supposed to include, which was 1 plus 2 plus 3 plus 4. Those are the terms that we're missing. So this sum, 1 to 50, is 50 times 51 over 2. And this sum, I could do quickly in my head. It's 10. The formula will also work, but 7, 8, 9, 10. Okay, so that comes out to 1,265. And then for an integer h greater than or equal to 2, I want to write out the sum for 1 plus 2 plus 3 plus blah, 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 up to h minus 1. So the last number, I'm adding the first h minus 1 integers. So h minus 1 is the last number in the list. So if I'm using this formula, the n is actually h minus 1. So I have to replace this n with an h minus 1 and this n with an h minus 1. So it's going to be h minus 1 times h minus 1 plus 1 over 2, which is h minus 1 times h over 2. A geometric sequence is one where each term of the sequence is obtained by multiplying the preceding term by some constant factor. If the first term is 1 and the constant factor is r, then the sequence would be 1 r squared, r cubed, r to the fourth. Just every term you multiply by r. 1 times r is r, times r is r squared, times r is r cubed, times r is r to the fourth. The next term would be r to the fifth, etc. So here's some examples of geometric sequences. These are powers of 2. The constant multiplier is 2. 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, etc. Here my constant multiplier is a third. 1 times a third is a third, times a third is a ninth, times a third is a 27th. And here my constant multiplier is 0.1. A tenth of 1 is 0.3, times a tenth is 0.03, times a tenth is 0.003, etc. So we have a formula for the first n terms of a geometric sequence, okay? Just like we have a formula for adding the first n integers, we have a different formula for adding the first n terms of a geometric sequence. I want to verify the geometric sum formula for when the constant multiplier r is 2 and n equals 4. So I wrote the formula down over here. But if my constant multiplier is 2, then my sum is the sum from I equals 0 to 4, because I'm doing 4 terms, n equals 4, of 2 to the I. My constant multiplier is 2. So this is 2 to the 0 plus 2 to the first plus 2 cubed. I skipped squared, plus 2 cubed plus 2 to the fourth. Okay, so that comes out to 31. And then I want to verify that if I put n equals 4 into this formula, I also get 31. So I have 2 to the 4 plus 1 minus 1 over 2 minus 1. So I'm putting 4 in for n and 2 in for r, just like they said here. Okay, and I get 2 to the fifth minus 1 over 1, which is 32, minus 1 over 1, which is 31. Okay, so it holds for r equals 2 and n equals 4. Okay, next I'm going to prove the geometric sum formula using mathematical induction. So remember that a proof by induction starts by proving the base case. So in this case, n equals 0. So I want to show that n equals 0. That means that I'm doing the sum from I equals 0 to 0 of r to the I. Does that equal r to the 0 plus 1 minus 1 over r minus 1? Now, this summation is just a single term, I equals 0 to 0. So you just plug in 0 and that's it, right? You start at 0 and you stop at 0. So this is r to the 0. So does r to the 0 equal r minus 1 over r minus 1? Okay, and the answer is yes, because both of these are 1. Anything to the 0 is 1, and anything over itself is 1. So we proved the base case. Okay, so now the induction step, we suppose that this is true for n equals k. Okay, so that means that I am assuming that this is true when I go from I equals 0 to k of r to the I, which translates to r to the 0 plus r to the first plus r squared plus r to the k. And I'm assuming for the n equals k case that this does in fact equal r to the k plus 1 minus 1 over r minus 1. So this is what I'm supposing. We're going to assume that this is true. And we need to show that it's true for n equals k plus 1. Okay, so I need to show that r to the 0 plus r to the first plus r squared plus all the way to the rk plus 1, which has to go through rk, that equals the formula plugging r to the k plus 1 as my last term. So k plus 1 is now my n. So this is going to be k plus 1 right here. So it's going to be k plus 1 plus 1. And that's it. Okay, so this is going to be r to the k plus 2 minus 1 over r minus 1. All right, so let's see if we can get there. So I'm going to say consider the sum that we're looking at. Okay, so I want r to the 0 plus r to the first plus r squared plus r to the k plus r to the k plus 1. Okay, so that equals, I can replace this bit with the formula, right? We are supposing that this sum is equal to this expression. So what I've underlined in orange here, I can replace with the formula that we are supposing is true. So I have r to the k plus 1 minus 1 over r minus 1. And then I still need to add the r to the k plus 1. Okay, now, again, just like in the last example, I have two fractions to add together, so I need a common denominator. So this r to the k plus 1 I'm going to make over 1, and I'm going to multiply by r minus 1 over r minus 1. Okay, so I have r to the k plus 1 minus 1 over r minus 1 plus. Now, I'm going to distribute this r to the k plus 1 to the r minus 1. Draw that in. So I have r to the k plus 1 times r, which is r to the k plus 2, because when you have like bases, you add the exponents. So this is r to the k plus 2 minus r to the k plus 1 over r minus 1. And now I have a common denominator, so I can just add the numerators. So I have an r to the k plus 1 minus an r to the k plus 1. So I get some cancellation here. That one and that one cancel out. So I am left with r to the k plus 2 minus 1 over the common denominator r minus 1. And that is precisely what I was trying to show. Okay, so I needed to show that this sum was r to the k plus 2 minus 1 over r minus 1, and that's what I ended up with. Okay, so to finish up this lesson, we're just going to practice using the geometric sum formula for a few sums here. So I have 1 plus 3 squared plus 3 to the m minus 2. So this is geometric with r equals 3, right? Because to get from one term to the next, I'm multiplying by 3. 1 times 3 is 3, times 3 is 3 squared, times 3 would be 3 cubed. And it's saying I'm just going to stop at m minus 2. So if I translate this into summation notation, this is going to be 3 to the I. I is going to start at 0 because 3 to the 0 will give me the 1. And then I'm going to stop at m minus 2. And then I'm going to apply this formula. So this says if you go from 0 to n of r to the I, in this case r is 3, it's r to the n plus 1 minus 1 over r minus 1. And then n plus 1 just means one bigger than wherever you stopped, right? We were stopping at n. N plus 1 is one bigger than that. So here I'm stopping at m minus 2. So when I plug into the formula, my r in this case is a 3. N is m minus 2, and then I'm going to add 1 to it. And then minus 1 over r minus 1. So this is 3 to the m minus 1 over 2. And then the next one, there's two ways I can approach this. It is geometric because 3 squared times 3 is 3 cubed, times 3 is 3 to the 4th. Then I'd get 3 to the 5th, 3 to the 6th, etc. until I get to 3 to the m. So one thing I could do is I could factor out a 3 squared to make this match this perfectly so that my first term would be a 1. So I could say, well, this is the same thing as 3 squared times 1 plus 3 squared plus dot 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 plus 3 to the m minus 2. And then what I have written in parentheses here is exactly what I just summed in part A. So this is just going to be 3 squared, which is 9, times 3 to the m, it's raised to the m, 3 to the m minus 1 over 2. Okay, so that's one way to approach that problem. Another way is to say, just going to go down here and say, or, you could say it's 1 plus 3 squared plus 3 cubed plus dot 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 all the way to 3 to the m, and that I have a formula for, right? And then I can subtract off the terms that are not in the original, right? So this started at 3 squared, so I can subtract off the 1 and the 3. Minus 1 plus 3, those two terms that I didn't need. So then the geometric sum is going to be, just apply the formula, 3 to the m plus 1 minus 1 over 2, and then minus 4. And we could get a common denominator and do some algebra and show that this and this expression are equivalent, but you don't need to do that. You can do one or the other procedure. They're equivalent.